Hello my friend, welcome back to the Sleepy Professor channel. I'm glad to see you again. Tonight we're going on a gentle journey through the cosmos, exploring one of the universe's most fascinating mysteries, black holes. Don't worry, we'll take our time moving slowly through each discovery, each wonder. There's no rush, no urgency, just the quiet contemplation of these extraordinary objects that exist in the darkness between the stars. Let your mind drift as we explore together. Get comfortable, settle in, close your eyes if you'd like, and let's begin this peaceful voyage through space and time. Breathe slowly, relax your shoulders, and allow yourself to float with me through the universe. You know, when most people think of black holes, they imagine something terrifying, a cosmic monster lurking in the darkness, ready to devour anything that comes near. But tonight, we're going to discover that black holes are so much more than that. They're laboratories where the laws of physics are pushed to their absolute limits. They're cosmic time machines, gateways that show us the deepest mysteries of reality itself, and perhaps most beautifully, they're proof that the universe is far stranger and more wonderful than we ever dared to imagine. So let's begin at the beginning with a simple question. What exactly is a black hole? Black holes aren't actually holes at all. They're regions in space where gravity has become so incredibly strong that nothing, not even light itself, can escape once it crosses a certain boundary. Imagine a sphere of ultimate gravity, pulling everything toward its center with an embrace that never lets go. It's a beautiful paradox, really, something we can never see directly, yet something that holds such immense, undeniable power in the fabric of our universe. Picture space itself as a flexible sheet, like a rubber membrane, and a black hole as a weight so heavy that it creates an infinitely deep pit in that sheet. Except this isn't just a metaphor. Space really does curve in this way, bending and warping around these mysterious objects. This strange thing is, if you could hold a black hole in your hand, which of course you couldn't, you wouldn't feel anything different from holding any other object of the same mass. A black hole with the mass of the Earth would have exactly the same gravitational pull as the Earth does at the same distance. It's only when you get very close that the extreme nature of a black hole becomes apparent. The density, the compactness, the concentration of mass into such a small space, that's what makes black holes unique and extraordinary. The term black hole was coined by physicist John Wheeler in 1967 during a conference in New York. Before this wonderfully evocative name, scientists called them things like frozen stars, or dark stars, or even collapsed objects. These earlier names were technically accurate but lacked poetry, lacked that immediate sense of mystery and wonder. Imagine sitting in that lecture hall in the 1960s, hearing this term for the first time, trying to wrap your mind around what it could possibly mean. Wheeler had a gift for language, and this name stuck because it captured something essential about these objects. Their darkness, their mystery, their profound strangeness. Sometimes the right words can change how we think about something entirely. The story of how we came to understand black holes is itself a fascinating journey through human thought and scientific discovery. It's a story that spans more than a century, connecting some of the greatest minds in physics through a chain of ideas and revelations. The boundary around a black hole, the point of no return, is called the event horizon. Such a poetic name when you think about it, isn't it? The horizon is where your view ends on Earth, where the sky meets the ground or sea, where you can see no farther. Here in space, the event horizon is where events cease to reach, you where information stops flowing outward to the rest of the universe. Cross this invisible line, and you've left our universe's ability to ever know what happens to you next. You become a secret kept by the cosmos itself, a story that can never be told, a message that can never be delivered. What's particularly fascinating is that the event horizon isn't a physical surface. There's nothing there, no wall, no barrier, no material substance. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the event horizon. You wouldn't even know you'd crossed it, at least not immediately. You'd just keep falling, and only later would you realize that you could never, ever go back. It's a mathematical boundary, a point in space defined purely by geometry and gravity, yet it has profound physical significance. It's the ultimate one-way street, the final door that can only swing inward. Albert Einstein's theory of general relativity, published in 1915, actually predicted black holes mathematically. Though Einstein himself was deeply skeptical they could really exist in nature. He spent years trying to prove they were merely mathematical curiosities, artifacts of the equations rather than real objects. It's comforting in a way that even Einstein, one of the greatest minds in human history, struggled to believe in something so profoundly strange. He published a paper in 1939 arguing that black holes couldn't form in the real universe. He was wrong, of course, but his skepticism was understandable. Black holes challenged even his revolutionary understanding of space and time. Sometimes reality is more imaginative than we dare to be, more willing to embrace the truly bizarre than even our most creative thinkers. Think about what this means for a moment. Einstein had just rewritten our understanding of gravity, showing that it wasn't a force pulling objects together, but rather a curvature of space-time itself. And even he couldn't quite accept where his own equations were leading. It would take decades of work by other physicists and eventually direct observations to convince the scientific community that black holes were real. The first theoretical description of what we now call a black hole came from Carl Schwarzschild in 1916, just months after Einstein published his theory of general relativity. What makes this even more remarkable is that Schwarzschild was serving in the German army during World War I when he made this calculation. There he was, in the trenches of one of humanity's darkest hours, surrounded by death and destruction, and his mind was exploring the darkest objects in the universe. The contrast is almost poetic. While the world around him was consumed by violence, his thoughts were reaching out to the stars, contemplating the most extreme conditions physics could imagine. He sent his solution to Einstein from the Russian front, a letter carrying equations that would change our understanding of the cosmos forever. Travelling from a battlefield to a university in Berlin, Schwarzschild would die just months later from an illness contracted during the war, pemphigus, a painful autoimmune disease. He was only 42 years old. His legacy, though, lives on in every black hole we study. The radius of a non-rotating black hole's event horizon is still called the Schwarzschild radius in his honour. Sometimes I think about how fitting it is that his name means black shield in German, almost as if fate had marked him for this discovery. He never lived to see how important his work would become, never witnessed the revolution in astrophysics that would follow from his calculations. There are actually different types of black holes, classified by how they formed and how massive they are. The smallest are stellar mass black holes, born from the collapse of individual stars. These are the black holes that form from the death throes of massive stars, the final punctuation mark at the end of a stellar life story. Then there are intermediate mass black holes, which we're still trying to understand. These mysterious objects, if they exist, would bridge the gap between stellar mass and supermassive black holes, and we're not entirely sure how they form or how common they are. And finally, there are supermassive black holes, millions or billions of times the mass of our Sun, lurking at the centres of galaxies. Each type tells a different story about the life cycle of the cosmos, about how matter and energy flow through the universe over billions of years. The range of masses is truly staggering when you think about it. From black holes just a few times the mass of our Sun to monsters that weigh billions of times more. It's like comparing a grain of sand to a mountain, except the difference is even more extreme, and each one formed through its own unique history, its own series of cosmic events. Stellar mass black holes form when massive stars, at least about 20 times the mass of our Sun, reach the end of their lives. The star runs out of fuel, and suddenly there's nothing to support it against its own gravity. For millions or even billions of years, the star has been locked in a battle. The outward pressure from nuclear fusion in its core pushing against the inward pull of its own gravity. It's a balance, a delicate equilibrium that can last for eons. But eventually, inevitably, the fuel runs out, the fusion stops, and in that moment, gravity wins decisively. In a fraction of a second, the core collapses, and if the star is massive enough, it doesn't stop collapsing. It just keeps going, compressing down past any possible stopping point, past the density of atomic nuclei, past any normal conception of matter, until it becomes a black hole. It's like the star falls into itself and disappears from our universe, leaving only gravity behind. The collapse happens so fast that if you could somehow watch it, you'd miss it in the blink of an eye. The core of the star, roughly the size of Earth, compresses down to a point, or at least to something so small that it might as well be a point. All that mass, all that matter confined to an impossibly tiny space. The physics of this collapse is still not completely understood, especially the final moments when quantum effects must become important. But we know it happens because we see the aftermath. When a star collapses into a black hole, most of its outer layers are blown off in a spectacular supernova explosion. These explosions can briefly outshine entire galaxies, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. Imagine that for a moment. Billions of years of steady sunshine, all compressed into a few seconds of unimaginable brilliance. The light from a single supernova can temporarily rival the light of 100 billion stars. And at the centre of all that light and fury, quietly a black hole is being born into darkness. It's one of nature's most dramatic ironies, the brightest event in the universe heralding the birth of its darkest object. These supernova explosions are also how the universe creates most of its heavy elements. The iron in your blood, the calcium in your bones, the gold in any jewellery you might wear. All of it was forged in stellar furnaces and scattered across space by supernovae. We are quite literally made of star stuff, and much of that star stuff was delivered to the universe by the same explosions that create black holes. In a sense, black holes and life are connected through this cosmic process of creation and destruction. The nearest known black hole to Earth is about 1,600 light-years away in a system called Gaia BH1. Now, 1,600 light-years might sound close in cosmic terms, but let me put that in perspective for you. If you could travel at the speed of light, which nothing with mass can do, it would still take you 1,600 years to reach it. That's longer than the entire history of the Roman Empire from founding to fall. Light that left that black hole system when the fall of Rome was still centuries in the future is only just now reaching our eyes. And if you tried to travel there in our fastest spacecraft, ones that travel at tens of thousands of kilometers per hour, it would take millions of years. We're quite safe here on our little blue planet, far from any black hole's grasp, protected by the vast emptiness of interstellar space. The discovery of Gaia BH1 was actually quite recent, announced in 2022. For a long time, we thought the nearest black hole was much farther away. But as our observational techniques improve, we keep finding more of these quiet, invisible objects lurking in our cosmic neighbourhood. There are probably many more stellar mass black holes relatively nearby that we simply haven't detected yet, because they're not actively feeding on anything or don't have a companion star to betray their presence. Despite their reputation, black holes don't actually roam around the galaxy, sucking up everything in their path like cosmic vacuum cleaners. They only affect things that come very close to them. This is one of the most common misconceptions about black holes, probably reinforced by science fiction movies and sensationalist headlines. The truth is much more nuanced and in its own way more interesting. If our sun were suddenly replaced by a black hole of the same mass, don't worry, this can't happen. Our sun isn't massive enough to ever become a black hole. The planets would continue orbiting exactly as they do now. We'd freeze without the sun's warmth and light, but Earth's orbit wouldn't change at all. Gravity would remain the same because the mass would remain the same. You see, gravity depends on mass and distance. A black hole only becomes extreme when you get very close to it, within a few times its event horizon radius. From far away, it's just another massive object. The black hole at the centre of our galaxy, despite being millions of times more massive than our sun, doesn't affect our solar system at all in any noticeable way. We orbit the galactic centre just as we would if that mass were distributed differently. The black hole's gravity, from our perspective 26,000 light-years away, is just gravity. The size of a black hole's event horizon depends on its mass. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers across. For a supermassive black hole like the one at the centre of our Milky Way galaxy, with a mass of about 4 million suns, the event horizon is about 25 million kilometers across, roughly 17 times the diameter of our Sun. These are the gates between our universe and whatever lies beyond. The more massive a black hole is, the lower its density at the event horizon. This seems counterintuitive, doesn't it? But it's true. A stellar mass black hole is incredibly dense, with enormous amounts of matter compressed into a tiny space. But a supermassive black hole spread across millions of kilometers can actually have a density similar to water at its event horizon. You could, theoretically, cross the event horizon of a supermassive black hole without even noticing initially. at least not until it was far too late to turn back. Inside a black hole, at its very centre, exists what physicists call a singularity, a point where matter is compressed to infinite density and volume becomes zero. At least, that's what our current equations tell us. But many physicists believe that our understanding breaks down at this point, and that quantum mechanics might step in to prevent true infinities. This singularity is where our best theories about the universe simply stop working, where the map of reality runs out of paper. Now, let's talk about something that sounds like pure science fiction, but is actually proven fact: the way time itself changes near a black hole. This is where things get truly mind-bending, where our everyday intuitions completely fail us. Time, that constant companion that seems to tick forward at the same rate for everyone, turns out to be far more flexible and strange than we ever imagined. Take a deep breath, because this next part is going to challenge everything you think you know about the nature of reality. Time behaves very strangely near a black hole. The closer you get to the event horizon, the slower time passes relative to someone far away. If you could hover just above the event horizon while your friend remained far away, and you stayed there for what felt like an hour to you, when you returned to your friend, they might have aged years or decades or even centuries, depending on exactly how close you got. Time itself bends in the gravity well of a black hole. You would return to find that your friend had lived an entire life while you experienced just an hour. Their children would have grown old. The world would have changed in ways you couldn't imagine. And from your perspective, you were only gone for 60 minutes. This isn't just theoretical speculation. This is what Einstein's equations tell us must happen, and we verified these predictions in countless experiments with atomic clocks and GPS satellites. The mathematics is unambiguous, even if the implications are deeply unsettling. Time is not the universal constant we once believed it to be. It's flexible, malleable, shaped by gravity just as space is. Imagine the profound loneliness of it, being separated from everyone you know, not by distance, but by time itself. You could be just a few kilometers above a black hole's event horizon, close enough to see the universe above you, and yet you'd be separated from that universe by an unbridgeable gulf of time. Every second for you would be hours or days for them. Any conversation would be impossible. By the time their words reached you, slowed and red-shifted by gravity, they'd be speaking from years in your future. This time dilation effect is called gravitational time dilation, and it's a real, measurable phenomenon. We actually have to account for it in GPS satellites orbiting Earth. Because they're farther from Earth's gravity than we are on the surface, time runs slightly faster for them, about 38 microseconds per day faster. It's a tiny effect, but if we didn't correct for it, GPS would become inaccurate very quickly. Black holes simply take this effect to an extreme we can barely imagine. If you were falling toward a black hole and looking back at the universe, you would see time in the outside universe speed up. Stars would live and die in what seemed like moments to you. Galaxies would spin faster and faster. If you fell into a supermassive black hole and could somehow look back, you might watch the rest of the universe age billions of years in what felt like minutes. You'd be watching the future unfold, racing forward to the end of time itself, all while falling into darkness. Stars would blink into existence and die in what seemed like moments. Galaxies would spiral and merge. The entire future history of the cosmos would play out before your eyes, like a time-lapse film, accelerating faster and faster as you fell deeper into the gravitational well. It would be the ultimate cosmic movie, and you'd have a front row seat, though it would also be the last thing you'd ever see. But there's something else we need to talk about. Something with a rather whimsical name that describes a decidedly unpleasant fate. There's a phenomenon called spaghettification. Yes, that's the real scientific term. That happens when something falls into a black hole. Because gravity gets stronger the closer you get to the source. Your feet, being closer to the black hole, would be pulled much harder than your head. The difference in gravitational force between your feet and your head would become enormous. You'd be stretched out like spaghetti, longer and thinner, pulled like taffy by forces that grow stronger with every meter you fall. Your body would elongate, first slowly, then faster and faster, until eventually you'd be torn apart at the atomic level. Every cell, every molecule, every atom would be pulled from its neighbours in an inexorable stretching that nothing could resist. For stellar mass black holes, this would happen long before you reach the event horizon. The gravitational gradient, the change in gravity over a short distance, is so steep that you'd be stretched and torn apart while still far from the point of no return. For supermassive black holes, though, the gradient is gentler. You might cross the event horizon intact and only be spaghettified as you approach the singularity deep inside. You'd have time to contemplate your situation, time to see the universe blue shift and speed up above you, time to wonder what awaits at the center, though ultimately the end would be the same. Dissolution into a stream of atoms falling toward the singularity. Black holes can spin, and many of them spin incredibly fast, some rotating hundreds of times per second. A spinning black hole is called a Kerr black hole, named after Roy Kerr, who solved Einstein's equations for rotating black holes in 1963. Roy Kerr was a New Zealand mathematician who succeeded where many others had failed, finding an exact solution to Einstein's field equations for a rotating mass. It's one of the most important solutions in all of general relativity, describing the space-time geometry around any rotating black hole in the universe. The spin of a black hole drags space-time around with it, creating a region called the ergosphere where nothing can remain stationary. Space itself is being pulled around the black hole like water swirling down a drain. Imagine standing on a moving walkway at an airport. You can walk against the direction of the walkway, but only up to a point. If the walkway moved fast enough, you wouldn't be able to stand still relative to the ground, no matter how hard you tried. The ergosphere is like that, except instead of a walkway moving through space, it's space itself that's being dragged around. Even a beam of light pointed directly away from the black hole would be swept around it. This phenomenon is called frame dragging, and it's one of the most exotic predictions of general relativity. The spinning black hole literally drags the reference frames, the coordinate systems we use to describe positions and motions, around with it. If you were in the ergosphere, you'd be forced to move in the direction of the black hole's rotation, pulled along by the spinning fabric of spacetime itself. The fastest spinning black hole we've detected is called GRS 1915 + 105, and it's spinning at least 950 times per second. Imagine that for a moment, an object with more mass than our Sun, spinning almost 1,000 times each second. The edge of its event horizon is moving at a significant fraction of the speed of light. The forces involved are difficult to even comprehend. Yet there it is, spinning in the darkness, a cosmic dancer that never slows down. Supermassive black holes live at the centres of most large galaxies, including our own Milky Way. Our galaxy's central black hole is called Sagittarius A star, pronounced Sagittarius A star, and it has a mass about 4 million times that of our Sun. It sits there in the centre of our galaxy, about 26,000 light-years away from us, holding court over the hundreds of billions of stars that orbit around it in a grand cosmic dance that's been going on for billions of years. For most of human history, we could only theorize about black holes, imagine them through mathematics and thought experiments. They were purely theoretical constructs, solutions to equations that might or might not exist in reality. But in recent years, we've entered a new era, an era where we can finally see these objects, or at least see their effects, with our own eyes and instruments. We actually captured the first ever image of a black hole in 2019. It wasn't Sagittarius A star though. It was a supermassive black hole in a galaxy called M87, about 55 million light-years away. M87 is a giant elliptical galaxy in the Virgo cluster, one of the largest and most massive galaxies in our cosmic neighbourhood. The black hole itself is about 6.5 billion times the mass of our Sun, a number so large it's difficult to truly comprehend. What we saw wasn't the black hole itself, of course. By definition, we can never see a black hole directly, but we saw the glowing ring of a hot gas swirling around it, with a dark shadow in the middle where the black hole sits. That shadow is larger than our entire solar system, larger than the orbit of Neptune. Light that would have passed through that region was instead captured by the black hole's gravity, leaving a dark circle surrounded by a brilliant ring of light. It was a moment when humanity finally saw, with our own eyes, what had been predicted a century earlier by Einstein's equations and Schwarzschild's mathematics. The image looked almost exactly like what computer simulations had predicted. Reality matched theory in the most spectacular way possible. When I first saw that image, I'll admit I was moved almost to tears. 100 years of theory, decades of technological development, and the coordinated effort of hundreds of scientists around the world, all culminating in that one blurry orange ring with a dark centre. It was proof that human curiosity and ingenuity could reach across 55 million light-years of space and capture something that seemed forever beyond our grasp. Creating that first black hole image required a global network of radio telescopes working together, effectively creating a telescope the size of Earth. They called it the Event Horizon Telescope. Teams around the world pointed their instruments at M87 for several nights, collecting petabytes of data. Then came the enormous task of processing all that data, which took 2 years. The final image was processed by Dr. Katie Booman and her team, using algorithms she'd developed specifically for this purpose. It was a triumph of human cooperation, ingenuity, and patience. In 2022, we finally got an image of our own galaxy's black hole, Sagittarius A star. Even though it's much closer to us than M87's black hole, it was actually harder to image. Why? Because material orbits around it much faster, making a complete orbit in just minutes rather than weeks. It's like trying to take a clear picture of a child running in circles compared to a slow walking adult. The gas around Sagittarius A star was changing on timescales faster than the observations, making the image blurry and difficult to reconstruct. Black holes aren't actually black in the way we might think. They don't absorb light because they are a dark colour. They absorb light because their gravity is so strong that light literally cannot escape. If you could somehow turn off a black hole's gravity, you wouldn't see anything there at all. There's no surface, no material, no thing in the conventional sense. A black hole is more like a region of space where the normal rules break down than it is like an object. The gas and dust swirling around a black hole before it falls in forms what's called an accretion disk. These disks can be incredibly hot, millions of degrees, because all that matter is crashing together at tremendous speeds, friction heating it up until it glows. The accretion disk around some black holes shines brighter than billions of stars combined. It's one of nature's beautiful ironies. The darkest objects in the universe surrounded by some of the brightest lights. Some black holes produce jets, powerful beams of particles and radiation that shoot out from near the black hole's poles at nearly the speed of light. These jets can extend for thousands or even millions of light years into space. We're not entirely sure how they form, but it involves the black hole's spin and powerful magnetic fields threading through the accretion disk. These jets are some of the most energetic phenomena in the entire universe, capable of affecting entire galaxies. When two black holes orbit each other and eventually merge, they create ripples in space-time itself called gravitational waves. Think of them as ripples spreading across the surface of a pond, except instead of water, it's the fabric of space and time itself that's rippling. These waves travel out from the merger at the speed of light, stretching and squeezing space itself as they pass. They're incredibly faint by the time they reach us. A gravitational wave passing through Earth might change the distance between 2 points by less than the width of an atomic nucleus across several kilometers, and yet we can detect them. In 2015, the LIGO Observatory detected gravitational waves for the first time from two black holes that merged over 1 billion light-years away. The detection came on September 14, 2015, and it was one of the most important scientific discoveries of the century. It was like hearing the universe ring like a bell, a sound that had travelled for over 1 billion years to reach us, carrying information about an event that happened when the Earth was still a planet of simple, single-celled life. The two black holes that merged were about 29 and 36 times the mass of the Sun, and they spiraled into each other in a final fraction of a second, releasing more energy than all the stars in the observable universe combined were producing at that instant. The gravitational waves from merging black holes give us information we could never get from light. They tell us the masses of the black holes, how fast they were spinning, and how far away the merger happened. It's like we've added a new sense to our perception of the universe. We can now feel its vibrations. Before 2015, we were effectively deaf to these cosmic events. Now we can listen to the universe in an entirely new way. When two black holes spiral toward each other in their final moments before merging, They're moving at a significant fraction of the speed of light, orbiting each other dozens or hundreds of times per second. In these final moments, they lose more energy to gravitational waves than all the stars in the observable universe are producing as light combined. It's a brief but incredibly intense display of nature's power, happening in darkness, announced to the universe only by ripples in space-time itself. There's a theoretical type of black hole called a primordial black hole that might have formed in the very early universe, shortly after the Big Bang. These wouldn't have formed from collapsing stars, but from regions of space where matter was so densely packed that it collapsed under its own gravity. If they exist, primordial black holes could be any size. Some might even be tiny, smaller than an atom but containing the mass of a mountain. They could be part of the mysterious dark matter that makes up most of the universe's mass. Now we come to one of the most beautiful and surprising discoveries in the entire history of physics, a discovery that connects quantum mechanics, thermodynamics, and gravity in a way that no one expected. This discovery changed how we think about black holes, how we think about the ultimate fate of the universe, and even how we think about the nature of information and reality itself. Stephen Hawking, in one of his most famous discoveries, showed in 1974 that black holes aren't completely black. They actually emit a very faint radiation due to quantum effects near the event horizon. This is called Hawking radiation, and it means that black holes very, very slowly evaporate over time. The discovery came from considering what happens when you apply quantum field theory, the quantum mechanical description of particles and fields, to the curved space-time near a black hole's event horizon. Here's how it works. In simplified terms, in quantum mechanics, what we think of as empty space isn't really empty. It's seething with virtual particles, pairs of particles and antiparticles that pop into existence and then annihilate each other almost instantly. Normally, these virtual particles exist for such a short time that they have no observable effect. But near a black hole's event horizon, something remarkable can happen. One particle of the pair might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles, radiation. And because energy is conserved, the black hole must lose a tiny amount of mass each time this happens. For a stellar mass black hole, this process would take longer than the current age of the universe many times over to have any significant effect. We're talking about temperatures of billionths of a degree above absolute zero, and evaporation times measured in googles of years, numbers so large that writing them in full would be impossible. But over unimaginably long time scales, even black holes will fade away, returning their energy to the universe. Nothing lasts forever, not even these most permanent seeming of objects. The temperature of Hawking radiation is inversely proportional to the black hole's mass. This means that larger black holes are actually colder than smaller ones. A supermassive black hole like the one in M87 has a temperature just a tiny fraction of a degree above absolute zero, colder than the cosmic microwave background radiation that fills space. It's so cold it actually absorbs more radiation from the universe than it emits. Only in the far, far future, when the universe has expanded and cooled further, will these giants finally begin to truly evaporate. As a black hole evaporates through Hawking radiation, it gets hotter, and as it gets hotter, it evaporates faster. Eventually, in its final moments, a black hole would explode in a burst of energy, but again, this is so far in the future that it's almost meaningless to us. We're talking about timescales of 10 to the 100th years or more, numbers so large that writing them out would be impossible. The universe as we know it will be long gone before even the smallest black holes from stars complete their evaporation. Black holes create what's called a gravitational lens. Their immense gravity bends light from objects behind them, sometimes creating multiple images of the same object, or stretching the image into rings called Einstein rings. This effect has allowed astronomers to study distant galaxies that would otherwise be too faint to see, using black holes as natural telescopes magnifying the universe beyond them. The darkness of a black hole, paradoxically, helps us see farther into the cosmos. There's something called the information paradox associated with black holes. When something falls into a black hole, all information about it, its quantum state, its history, everything that makes it what it is, seems to be lost forever. But quantum mechanics says information can't be destroyed. So what happens to it? Does it truly disappear? Is it encoded on the event horizon? Does it leak out slowly through Hawking radiation? Physicists have been debating this for decades, and we still don't have a definitive answer. It's one of the deepest mysteries in physics. Some scientists have proposed that what we perceive as a black hole might actually be something else, perhaps what they call a fuzzball, where quantum effects prevent the formation of a true singularity. Or maybe the event horizon isn't quite as sharp as we think, but is instead a fuzzy boundary where quantum mechanics becomes important. We won't know for sure until we can combine general relativity and quantum mechanics into a complete theory of quantum gravity, something physicists have been working toward for decades. Inside a black hole, space and time swap roles. Outside a black hole, you can move freely through space but are forced to move forward in time. Inside a black hole, you're forced to move toward the singularity. It's as inevitable as tomorrow becoming today. But the direction of time becomes something you could theoretically move through. It's one of the most mind-bending aspects of black holes, and honestly, it's difficult for our human brains to fully grasp. Our everyday experience gives us no intuition for such situations. The supermassive black hole at the center of the M87 galaxy is so massive that if you replaced our Sun with it, its event horizon would extend beyond Neptune's orbit. The entire solar system, out to the farthest planet, would fit inside this black hole with room to spare. And yet, from our perspective, 55 million light years away, even with our most powerful telescopes working together, it appears as a small dark circle, a shadow cast against glowing gas. Black holes can collide with neutron stars, incredibly dense stellar remnants that aren't quite massive enough to collapse into black holes. When this happens, the neutron star is torn apart by tidal forces, and pieces of it swirl around the black hole before falling in. These collisions also produce gravitational waves, which we've now detected several times. Each detection tells us more about the population of these extreme objects in our universe, slowly filling in our census of the cosmos's most exotic residents. There might be intermediate mass black holes, with masses between stellar mass and supermassive black holes. These would be thousands to hundreds of thousands of times the mass of the Sun. We have hints of their existence, but haven't confirmed them definitively yet. If they exist, they might be the seeds that eventually grow into supermassive black holes, or they might form through different processes entirely. They're one of the missing pieces in our understanding of how black holes form and evolve over cosmic time. Some scientists think that supermassive black holes might have formed directly in the early universe from massive clouds of gas collapsing all at once, rather than from stars. This would help explain how we see such massive black holes so early in cosmic history. There simply hasn't been enough time for them to grow from stellar mass black holes through normal accretion and mergers. The early universe, it seems, might have been a more violent and extreme place than we once thought. The event horizon of a black hole is one of the most perfect spheres in nature. Any lumpiness or deviation from a sphere would radiate away as gravitational waves almost instantly. This property is called the no-hair theorem in physics. It states that black holes can only be described by three properties: mass, spin, and electric charge. Everything else, all the complexity of what fell in, is lost. Black holes are, in a sense, the simplest macroscopic objects in the universe. Despite the no-hair theorem, recent observations have shown that the space outside a black hole can be quite complex, with swirling patterns of gas, magnetic fields, and radiation. It's the black hole itself that's simple, not its environment. That environment, the accretion disk, the jets, the orbiting stars, can be incredibly rich and varied. Each black hole exists in its own unique context, shaped by its history and surroundings. There are stellar mass black holes that are part of binary systems, orbiting a normal star. We can detect these black holes by watching how they affect their companion. Sometimes they pull gas off the companion star, which forms an accretion disk and produces X-rays. Sometimes we can see the companion star wobbling in its orbit, pulled by an invisible massive companion. These binary systems are like cosmic laboratories, allowing us to study black holes through their gravitational influence on nearby matter. One such binary system, called Cygnus X1, was the first strong candidate for containing a black hole. Discovered in 1964, it took years of observations and debate before astronomers were confident it really contained a black hole. Stephen Hawking famously bet physicist Kip Thorne that Cygnus X1 didn't contain a black hole, and conceded the bet in 1990 when evidence became overwhelming. Sometimes even the experts need convincing when faced with something as strange as a black hole. The escape velocity from a black hole's event horizon is exactly the speed of light. That's why nothing can escape. You'd need to travel faster than light, which is impossible according to our current understanding of physics. As you get farther from a black hole, the escape velocity decreases. At Earth's distance from the Sun, if you replace the Sun with a black hole of the same mass, the escape velocity would be exactly the same as it is now, about 42 kilometers per second. Light orbiting right at the edge of what's called the photon sphere, just outside the event horizon, can orbit a black hole. At this precise distance, light travels in circles round the black hole. Closer than this, and even light must spiral inward. Farther out, and light can escape to infinity. The photon sphere is like a circular prison for light, where photons endlessly chase each other around the black hole in perfect circles. If you could somehow survive at the photon sphere and look in any direction, you'd see the back of your own head. Light from the back of your head would orbit around the black hole and come back to your eyes. You'd see infinite copies of yourself, each one wrapping around the black hole multiple times. It would be the strangest hall of mirrors imaginable, created by gravity bending light into loops. The supermassive black hole at the center of our galaxy is relatively quiet right now. It's not actively feeding on a lot of material, so it's not producing huge amounts of radiation. But about 3.5 million years ago, recent in cosmic terms, there's evidence it was much more active, producing a huge burst of energy that created giant bubbles of hot gas extending above and below the plane of our galaxy. These are called the Fermi bubbles, and we can still detect them today with gamma-ray telescopes. Some galaxies have active galactic nuclei, or AGN, where the supermassive black hole is actively feeding and producing tremendous amounts of energy. These can outshine all the stars in the galaxy combined. Quasars are the most luminous type of AGN, and they can be seen across the entire observable universe. The most distant quasars we've detected show us black holes that existed when the universe was less than 1 billion years old, already grown to billions of solar masses. They're like beacons from the early universe, lighthouses in the cosmic dark. The word quasar is actually short for quasi-stellar radio source. When they were first discovered in the 1960s, astronomers were puzzled by these radio sources that looked like stars in optical telescopes but were clearly something else. It took years to figure out that they were actually distant galaxies with incredibly active supermassive black holes at their centers. Sometimes the simplest observations lead to the most profound discoveries. Material falling into a black hole doesn't fall straight in. Conservation of angular momentum means it spirals inward, forming the accretion disk. This disk can be incredibly thin relative to its diameter, thinner than a sheet of paper is to a football field. And yet within this disk, temperatures reach millions of degrees, and magnetic fields strong enough to power jets are generated. It's a structure of remarkable complexity arising from simple physical laws. Some black holes produce what are called quasi-periodic oscillations, or QPOS, repeating patterns in their X-ray emissions that occur on timescales of milliseconds to seconds. These oscillations are thought to be related to structures in the inner accretion disk, perhaps spiral waves or hot spots orbiting close to the event horizon. By studying these oscillations, astronomers can probe regions very close to the black hole, testing our theories of gravity and the strongest gravitational fields we know of. There's a maximum rate at which a black hole can accrete matter called the Eddington limit. Above this rate, the radiation pressure from all the light being produced would push away any additional matter trying to fall in. And yet, we've observed black holes that seem to be exceeding this limit, somehow managing to grow faster than we thought possible. Nature, it seems, has tricks we haven't fully figured out yet. The gravity near a black hole is so strong that it redshifts light. Light climbing out of the gravitational well loses energy, shifting to longer, redder wavelengths. Light from material very close to a black hole can be redshifted dramatically, sometimes becoming invisible in the optical spectrum and only detectable in X-rays or radio waves. It's like the light is climbing up a mountain, arriving at the top exhausted, depleted of energy. Black holes can also blue shift light if the material is moving toward us at high speeds. In an accretion disk, material on one side is moving toward us and on the other side moving away. This creates a characteristic asymmetry in the emission, one side brighter and bluer, the other dimmer and redder. By studying this asymmetry, we can measure how fast the black hole is spinning, probing its fundamental properties from thousands or millions of light years away. when a star passes too close to a supermassive black hole, tidal forces can tear it apart in what's called a tidal disruption event. About half the star's material is flung away into space, while the other half falls into the black hole, creating a temporary accretion disk and a burst of radiation. We've observed several of these events, each one giving us a glimpse of a star's final moments as it's destroyed by gravity itself. These tidal disruption events can last for months or years as the stellar debris settles into an accretion disk and falls into the black hole. They're like fireworks on a cosmic scale, announcing the death of a star in a brilliant but temporary display. Then the black hole settles back into quiescence, waiting for its next meal, which might not come for thousands or millions of years. Not every star that passes close to a supermassive black hole is destroyed. Some are merely flung away at high speeds, becoming what astronomers call hypervelocity stars. These stars are travelling so fast, sometimes over 1,000 kilometers per second, that they'll eventually escape the galaxy entirely, wandering alone through intergalactic space. They're exiles, thrown out of their home galaxy by a close encounter with the central black hole. The region very close to a black hole's event horizon, where orbits are unstable and material is spiraling in, is sometimes called the plunging region. Once matter enters this region, there's no more spiraling outward, no more hovering. It's a one-way trip to the event horizon and beyond. It's the region where fate is sealed, where the future becomes inevitable. Some physicists have speculated about whether it might be possible to extract energy from a rotating black hole. There's a process called the Penrose process where, in principle, you could drop something into the ergosphere of a spinning black hole in just the right way that it splits, with one piece falling in and the other escaping with more energy than you started with. The black hole's rotation would slow down very slightly, and that rotational energy would be transferred to the escaping piece. It's speculative and likely impractical, but theoretically possible according to our understanding of physics. If an advanced civilization wanted to power itself using a black hole, they could in principle build a structure around it to capture the energy from the accretion disk or from jets or from the Penrose process. Such a civilization would have access to enormous amounts of energy, far more than you could get from stars. Some scientists have speculated that we might eventually detect such advanced civilizations by looking for the waste heat from these black hole power plants. It's one way we might search for life far more advanced than our own. Inside a rotating black hole, the structure is more complex than in a non-rotating one. There are actually two event horizons, an outer and an inner one, and a region between them where strange things happen. There's even a theoretical region called the Cauchy horizon, where, according to our equations, you might experience infinite tidal forces. But most physicists believe that something, perhaps quantum effects, would prevent you from ever reaching this region. Our equations break down before the predictions become truly infinite. Some rotating black hole solutions to Einstein's equations contain closed time-like curves, paths through space-time that loop back on themselves. If you followed one of these paths, you'd end up back where and when you started, having travelled through time. But most physicists believe that something, probably quantum effects that our current theories don't fully capture, would prevent these from actually forming in nature. Time travel backwards remains in the realm of speculation and science fiction, at least for now. When we observe very distant black holes, we're also looking back in time. Light takes time to travel, so a quasar 12 billion light years away shows us what that black hole was doing 12 billion years ago, when the universe was young. In a very real sense, we're seeing into the past, watching how black holes and galaxies evolved over cosmic history. Every observation of a distant black hole is also a time machine, showing us the universe as it once was. The distribution and properties of black holes tell us about the history of star formation in the universe. Where there are black holes, there were once massive stars. By studying black holes across cosmic time, we're reading the fossil record of stellar evolution, learning about the lives and deaths of stars that burned billions of years ago in galaxies far away. Some black holes are moving through space at high speeds, either because they were kicked by the asymmetric emission of gravitational waves during a merger, or because they are in binary systems with stars. These wandering black holes might occasionally pass through interstellar clouds, accreting material and briefly lighting up. There might be many stellar mass black holes drifting through the galaxy that we simply haven't detected yet, because they're not currently feeding on anything. The Milky Way likely contains tens of millions to 100 million stellar mass black holes, the remnants of massive stars that have died over the galaxy's billions of years of history. Most of them are completely isolated, invisible in the darkness of space. We've only detected a few thousand because we can only see the ones that are either in binary systems or actively accreting material. The rest are silent, invisible, known only through theoretical predictions. When material falls into a black hole, up to about 40% of its mass can be converted to energy, primarily through the heating of the accretion disk. This is far more efficient than nuclear fusion in stars, which converts less than 1% of mass to energy. In terms of pure energy extraction from matter, black holes are the most efficient power sources in the universe. If we could somehow harness them, they'd be the ultimate power plants. The shadow of a black hole, the dark region we see in images like the one from the Event Horizon Telescope, is actually about 2.5 times larger than the event horizon itself. This is because light from behind the black hole is bent around it, and there's a region where light is bent so strongly that it orbits the black hole multiple times before escaping. The shadow represents not just the event horizon, but the photon sphere around it, the region where light's path is most strongly affected by the black hole's gravity. If you watched someone fall into a black hole from a safe distance away, you would never actually see them cross the event horizon. Due to time dilation, their clock would appear to slow down more and more as they approached the horizon. They would appear to freeze, their image becoming redder and dimmer, eventually fading from view. From your perspective, they would hover forever at the edge of the black hole, though from their own perspective, they would cross the horizon and continue falling inward in a finite time. This means that, in a sense, from our perspective outside the black hole, nothing has ever actually fallen past the event horizon. Everything that's ever approached a black hole is still hovering at the horizon, frozen in time from our point of view. Only from the infalling material's perspective has it crossed over. Different reference frames see fundamentally different realities near a black hole. It's one of the most profound ways that relativity shows us how subjective our experience of time really is. The study of black holes has helped us understand that space and time aren't separate things, but are woven together into space-time, a four-dimensional fabric that can be bent and stretched by gravity. Before Einstein, we thought of space as an empty stage where events played out, and time as a universal clock ticking forward. Now we know that space and time are dynamic, responsive to matter and energy, curved by gravity. Black holes are where this curvature becomes extreme, where the fabric of space-time is stretched almost to breaking. Some theoretical physicists have explored the possibility that black holes might be connected to other regions of space through wormholes, shortcuts through space-time. If two black holes were connected by a wormhole, you might fall into one and emerge from another, potentially in a completely different part of the universe, or even a different universe altogether. But these wormholes, if they exist at all, are probably microscopic and unstable, collapsing before anything could pass through them. It's a beautiful idea, but nature may not actually allow it. There's a deep connection between black holes and thermodynamics. Black holes have a temperature, as Hawking showed, and they have entropy proportional to the area of their event horizon. In fact, the entropy of a black hole is enormous, the largest entropy of any object of a given volume in the universe. This suggests that black holes are, in some sense, the most disordered or information-rich objects that can exist. The connections between black holes, thermodynamics, and information theory hint at deep truths about the nature of reality that we're still working to fully understand. The holographic principle, inspired by the study of black holes, suggests that all the information in a volume of space can be encoded on the boundary of that space like a hologram. This radical idea suggests that our three-dimensional reality might be in some sense a projection from a two-dimensional surface. It's one of the strangest ideas to come out of modern physics, and it all started from thinking carefully about what happens to information in black holes. String theory, one attempt to unify quantum mechanics and gravity, predicts that black holes might be made of vibrating strings of energy. In this view, what we perceive as a black hole is actually a dense tangle of these fundamental strings. Different vibration patterns of strings would correspond to different particles and forces. It's a beautiful, elegant idea, though we don't yet have experimental evidence to confirm whether string theory correctly describes our universe. Some versions of string theory predict that there might be extra dimensions of space beyond the three we experience. Black holes in these higher dimensional theories can have different properties than in our familiar four-dimensional space-time. If there are extra dimensions, black holes might be the key to detecting them, as they would affect how black holes form and behave. The universe might be more complex and strange than even our wildest theories suggest. The study of black holes has revealed that our universe might have fundamental limits on how much information can be contained in a region of space. This is called the Bekenstein bound, after physicist Jakob Bekenstein, who showed that the maximum entropy of any region is proportional to its surface area, not its volume. Black holes saturate this bound. They contain the maximum possible entropy for their size. It's as if the universe has a fundamental resolution, a graininess at the smallest scales that limits how much information can exist. When two black holes merge, they produce gravitational waves with a characteristic chirp. The frequency increases as the black holes spiral closer together, then drops abruptly when they merge, followed by a ring down as the merged black hole settles into its final state. This chirp encodes information about the masses and spins of the black holes, and the ring down tells us about the properties of the final merged black hole. By analysing these signals, we can test general relativity in its most extreme conditions. The network of gravitational wave detectors around the world, LIGO in the United States, Virgo in Italy, Kagra in Japan, allows us to pinpoint where in the sky a gravitational wave came from by measuring the tiny differences in arrival time at different detectors. It's like triangulation with time differences measured in milliseconds. With more detectors, we can locate sources more precisely, helping optical telescopes to search for any accompanying light from the event. Some black hole mergers produce no light at all, just gravitational waves. These are called dark sirens. They're events happening in darkness, announced to us only by the ringing of space-time itself. Other mergers, particularly those involving neutron stars or a black hole and neutron star, can produce brilliant displays of light across the electromagnetic spectrum. These bright sirens let us study the event with both gravitational waves and traditional telescopes, giving us a more complete picture. The energy released in gravitational waves from a black hole merger can be staggering. In one merger detected by LIGO, about 3 solar masses worth of energy were radiated away as gravitational waves in less than a second. That's 3 entire suns worth of mass converted to pure energy in a fraction of a second. More power than all the stars in the observable universe combined were producing at that moment. And this happens in darkness, silently, announced only by ripples in space-time. Black holes can exist in what's called a quasi-stable orbit, where 2 black holes orbit each other for an extended period before finally merging. During this time, they're slowly radiating energy as gravitational waves, which causes the orbit to shrink gradually. The closer they get, the faster they orbit, and the more gravitational waves they produce, which makes them spiral in even faster. It's a runaway process that leads inevitably to merger, but it can take billions of years for the final plunge to occur. Some supermassive black hole binaries might be stalled in their merger. If they're in a galaxy that doesn't have much gas or many stars around the center, there might not be enough material to carry away energy and angular momentum, which would allow the black holes to merge. These stalled binaries could persist for billions of years, 2 supermassive black holes locked in orbit around each other at the center of a galaxy. We've found a few candidates for such systems, but they're difficult to confirm. When we observe the jets from black holes, we sometimes see them moving faster than light. At least that's what it looks like. This is an illusion caused by the geometry of the observation. If a jet is moving toward us at nearly the speed of light, the light it emits later in its path doesn't have to travel as far to reach us, so it arrives shortly after the light emitted earlier. This makes it appear that the jet is moving faster than light. It's called superluminal motion, and it's a beautiful consequence of special relativity combined with geometry. The magnetic fields around black holes can be extraordinarily strong. These fields are generated by the motion of charged particles in the accretion disk, and can become organized into complex structures. They're thought to be crucial for launching jets and for regulating how material falls into the black hole. Understanding these magnetic fields is one of the frontiers of black hole research. requiring sophisticated computer simulations to model their behavior. Some black holes produce what are called microquasars, smaller-scale versions of quasars in our own galaxy. These are stellar mass black holes with jets feeding on matter from a companion star. They give us the opportunity to study jet physics in detail, watching how the jets change over days or weeks rather than the millions of years it would take to see changes in a distant quasar. They're like laboratories for understanding the physics of jets and accretion. The spin of a black hole can be measured by studying the inner edge of the accretion disk. For a non-rotating black hole, stable orbits can exist down to 3 times the Schwarzschild radius. For a maximally rotating black hole, stable orbits can exist much closer, less than 1 Schwarzschild radius from the center. By measuring where the inner edge of the disk is, we can infer how fast the black hole is spinning. Some black holes are spinning at close to the maximum possible rate, while others spin slowly or not at all. There's a prediction that if you could watch material orbit very close to a black hole, you'd see multiple images of it due to light bending around the black hole. You might see the same blob of hot gas appearing multiple times in your image, once from light that came directly to you, once from light that went halfway around the black hole first, once from light that went completely around, and so on. These would be like echoes of the same object, arriving at different times. With our current telescopes, we can't quite resolve these features yet, but future observations might be able to detect them. The study of black holes has implications for the ultimate fate of the universe. If the universe continues to expand forever, eventually all the stars will burn out and black holes will be among the last objects remaining. Over incomprehensible timescales, even these will evaporate through Hawking radiation, until nothing is left but particles drifting through an ever-expanding, ever-cooling void. It's a bleak picture, but it's billions upon billions of years away, so far in the future that the universe as we know it now will be unrecognizably different long before that end comes. Some physicists have proposed that new universes might be born inside black holes. In these theories, the singularity might not be an endpoint, but a gateway to a new region of space-time, a new universe expanding with its own Big Bang. Our universe might itself have been born inside a black hole in another universe. It's a speculative idea, and we may never be able to test it, but it's a reminder that black holes might not be endings but transitions, passages from one reality to another. Black holes have even influenced our thinking about quantum mechanics. The information paradox and related puzzles have led to ideas like black hole complementarity, the firewall paradox, and ER equals EPR, a proposed connection between wormholes and quantum entanglement. These ideas suggest deep connections between gravity, quantum mechanics, and information that we're still working to understand. Black holes sit at the intersection of our 2 most successful theories, general relativity and quantum mechanics, and they're where the contradictions between these theories become impossible to ignore. The largest black holes we know of are ultra-massive black holes, with masses tens of billions of times that of the Sun. The black hole in the centre of the galaxy, Holmberg 15A, might be around 170 billion solar masses. At that scale, the event horizon is larger than the orbit of Neptune. The entire solar system out to the edge could fit inside with room to spare. These objects are almost beyond comprehension. gravity wells so deep that they define the centers of entire galaxy clusters. Not all galaxies have supermassive black holes at their centers, or at least, not all have black holes as massive as we might expect. Smaller galaxies tend to have smaller or sometimes no central black holes. There's a relationship between the mass of a galaxy's central bulge and the mass of its central black hole. This suggests that galaxies and their central black holes grow together, co-evolving over billions of years in a process we're still working to fully understand. When galaxies merge, their central black holes eventually merge too, but this can take billions of years. The black holes initially are too far apart to interact directly. They sink toward the center of the merged galaxy, slowed by dynamical friction with surrounding stars. Eventually they form a binary, orbiting each other, slowly losing energy to gravitational waves until they finally merge. Each merger makes the black hole more massive, and over cosmic time, this is how supermassive black holes grow to their enormous sizes. Some black holes are thought to be the endpoints of very massive stars called population 3 stars, the first generation of stars to form after the Big Bang. These stars, formed from hydrogen and helium, alone with no heavier elements, could be hundreds of times the mass of the Sun. When they died, they might have collapsed directly to black holes without a supernova explosion, creating the seeds that eventually grew into the supermassive black holes we see in distant early galaxies. The future holds exciting possibilities for black hole research. New gravitational wave detectors like the planned space-based LISA will be able to detect supermassive black hole mergers across the universe. Next-generation radio telescope arrays might image black holes with much higher resolution, showing us the details of jets and accretion flows. And theoretical advances in quantum gravity might finally resolve the deepest puzzles about what happens at singularities and event horizons. We're living in a golden age of black hole science, and the best is likely yet to come. Black holes remind us of how much we still don't understand about the universe. They push our theories to their limits, forcing us to confront questions about the nature of space, time, matter, and information. They're puzzles wrapped in mysteries, cloaked in darkness, yet they're also real objects we can observe and study. They exist in that liminal space between the known and the unknown, the understood and the mysterious. Sometimes, late at night, I think about what it would be like to approach a black hole. Not the mathematical description, not the equations, but the actual experience. You'd see the stars behind it distorted, pulled into strange shapes by the bending of light. You'd see multiple images of the same stars as light took different paths around the black hole to reach you. The black hole itself would appear as a perfect circle of absolute darkness, darker than anything you've ever seen, because it's not just an absence of light, but a region where light cannot exist at all. As you got closer, you'd feel the tidal forces beginning to pull at you. Time would start to behave strangely. You'd see the universe outside speeding up, aging before your eyes. The stars would race through their life cycles, galaxies would spiral and merge, and then, if you got close enough, you'd cross the event horizon. From your perspective, nothing would change at that moment. You'd feel no barrier, see no wall, you'd just keep falling. But you would have passed a point of no return, a boundary in space-time itself. Everything in your future would lead inevitably toward the singularity at the center. What happens at that singularity, we don't know. Our equations break down, giving us infinities and impossibilities. Maybe quantum gravity resolves the singularity into something else, something finite. Maybe there's a bounce, a transition to another region of space-time. Or maybe there really is an endpoint where everything that falls in is compressed to infinite density. We don't know, and there's no way to find out. Anything that crosses the event horizon can never send information back to us. The singularity keeps its secrets. This uncertainty, this unknowing, is part of what makes black holes so compelling. They represent the limits of human knowledge, the boundaries where our best theories fail. And yet we keep studying them, keep pushing those boundaries, keep trying to understand. Because that's what humans do. We explore, we question, we seek to understand even the most incomprehensible things. Perhaps the most profound thing about black holes is what they teach us about the universe's essential strangeness. We live in a cosmos where space and time can be stretched and bent, where objects can exist that trap light itself, where the rules of physics as we know them break down. Black holes are reminders that reality is far stranger and more wonderful than our everyday experience suggests. They invite us to question, to wonder, to explore. And in that invitation they remind us why we look up at the stars in the first place. Not just to understand, but to be amazed. Every black hole in the universe has its own story. Each one was formed through a unique sequence of events, a particular stellar death, or collision, or primordial collapse. Each one sits in its own corner of space, interacting with its own environment, affecting the stars and gas around it in its own way. And each one holds secrets that we may never fully uncover, information about everything that has ever fallen into it, compressed and hidden behind the event horizon. In a sense, black holes are the universe's great archivists, storing the history of everything they've consumed. But they're archivists who never share their secrets, librarians who guard their books jealously against all who would read them. The information that falls into a black hole becomes inaccessible to the outside universe, locked away perhaps forever, or perhaps slowly leaking back out through Hawking radiation in a scrambled, unreadable form. We don't know which. It's one of the great unsolved mysteries of physics. And yet, despite all the mystery, despite all the unanswered questions, we've learned so much about black holes in recent decades. We've detected their gravitational waves, seen their shadows, measured their spins and masses, watched them tear apart stars and accelerate jets to nearly the speed of light. We've gone from wondering whether they exist at all to studying them in detail, from pure theory to observation. It's been one of the great triumphs of human scientific endeavour. As you drift off to sleep tonight, you can rest knowing that out there, scattered throughout the cosmos, these remarkable objects are continuing their eternal dance. Some are spinning hundreds of times per second. Some are colliding and merging, sending gravitational waves rippling through space-time. Some are feeding on gas and dust, surrounded by brilliant accretion disks, and some are simply drifting through the darkness, invisible and silent, patiently waiting for something to fall within their grasp. They're all doing their part in the grand cosmic story, shaping galaxies, creating jets, perhaps even giving birth to new universes in ways we don't yet understand. Black holes connect the very largest scales of the universe, galaxies and cosmology, with the very smallest, quantum mechanics and the fundamental nature of information. They're bridges between disciplines, between theories, between the known and the unknown, and they'll continue to be sources of wonder and discovery for generations to come. Thank you for spending this time with me, exploring these dark wonders of the cosmos. I hope your mind is peaceful, your thoughts drifting like starlight across the vast darkness of space. Tonight, as you close your eyes, remember that you're lying on a planet that's orbiting a star, which is orbiting the center of a galaxy, where a supermassive black hole sits patiently at the heart of it all. You're part of this vast cosmic dance, connected to everything from the smallest quantum particles to the largest structures in the universe. Rest well, my friend, knowing that the universe is far more beautiful and mysterious than we can fully comprehend. Let the wonder of it all wash over you like a gentle tide, carrying you softly into sleep. The black holes will still be there tomorrow, spinning and merging and bending space-time, waiting for us to learn more of their secrets. But for now, it's time to rest. Time to let your mind drift among the stars. Sweet dreams, and until next time, good night.